What is electric current? In essence, it is the flow of electricity. And it's akin to water flowing through a pipe. So imagine a wire, like a pipe, and it has electrons in it. Well, if the wire isn't connected to anything, the electrons just randomly move in all sorts of directions, traveling at millions of meters per second. The motion is all random. But if you take that wire and you connect it to a voltage source, voltage is also known as potential difference or electromotive force, EMF, the force due to the electric field induced by the battery will cause the electrons to move through the conductor. Now, if you notice, the electrons are moving through the conductor from the negative towards the positive sides of the battery. Well, electrons are negatively charged, so they'll be attracted to the positive end of the battery. And we define current as flowing from the positive to the negative end. In other words, we define current to move in the direction opposite to the electron flow. So by convention, electric current is defined as the movement of positive charge, not negative charge, positive charge, which is opposite to the drift of the electrons. Now there's a story behind this. Benjamin Franklin, who was the first to experiment with positive and negative charges, he discovered that there were two opposite charges, but he didn't know which was which. So he randomly said, well, let's call this one positive and this one negative. And once the electron was discovered, we found out that Benjamin Franklin made an unfortunate choice. And we've never changed that convention, we just kind of roll with it. So using this convention, the current moves from the positive towards the negative pole of the electromotive force. Also, in this case, would be the battery. So here I have a diagram of a light bulb. It's just a picture of a light bulb. Light bulb is connected to the bottom and to its side by wires, and that's connected to a battery. The symbol for a battery are these two bars. The longer of the two is the positive side of the battery, and the short is the negative side of the battery. And like I've stated, the current moves from the positive pole of the battery through the circuit back into the negative side of the battery. So more on current and how we define it. Current is the amount of charge, positive charge, that moves through the cross-sectional area of the wire per unit time. So here's a diagram of a wire, sliced. There's the cross-section. And when we talk about calculating current or measuring current, we're talking about these positive charges passing through this wire, through this pipe, kind of like water passing out of a hose. That would be our current. And current would be charge per unit time. The charge, Q, is measured in coulombs, capital C. Time is in seconds, small s. So current would be coulombs per second, and 1 coulomb per second is defined as the ampere, or we just say amps. So the electrons, or protons, depending on how you want to view this, are the carriers of electric current. So if we're viewing this as the flow of electrons, well, one electron has a charge of negative 1.6 times 10 to the minus 19 coulombs. If you view this model as the current model, one proton would be positive 1.6 times 10 to the minus 19 coulombs. Remember, electrons and protons are oppositely charged. In chemistry, you said positive 1 and negative 1. Well, the actual charge are these two numbers, okay? Just opposite in signs. So here's an example. Here we have a light bulb connected to a battery, and we have current flowing from the positive end to the negative end of the battery through the light bulb. And as the current moves through the light bulb, it causes the light bulb to light up. So we have 3.75 coulombs of charge moving through the filament of the light bulb in 5 seconds. So the first question is, what is the current through the light bulb? So we can use the equation I gave you. Current is charge per unit time. The charge is 3.75 coulombs. The time is 5 seconds. Therefore, the current through the light bulb is 0.75 amps. Now the next question, how many electrons pass through the filament in 5 seconds? Well, we can use dimensional analysis to answer this question. There's no formula. You just look at what the problem is. And the question is, how many electrons per second? So that's what we want to end up with, electrons per second. So we know that one electron has a charge of 1.6 times 10 to the minus 19. And we know that we have 3.75 coulombs of charge traveling through a time of 5 seconds. So we set up the dimensions such that the coulombs cancel, and we're left with electrons per second, which is 4.69 times 10 to the 19 electrons every second.